Appreciate you joining. You said October of 2021. I thought it was like a couple of months ago. So that means I'm having a lot of fun. So since I talked to you, we've launched, and I'll talk more about that. And we're in the commissioning phase, and you hear a lot about that towards the back end. So let's just dig right in. So first few charts are reminders for the ones who've heard some of this before, and then some is a repeat, and some is new. So the primary purpose of James Webb is to look back at the early formation of our universe in the 100, 200, 300 million years after the Big Bang, which still blows my mind that we can look back and see stars and galaxies forming in that time frame. And some of you may remember a month or so ago, maybe 6 weeks, Hubble actually found a star that was 900 million years after the Big Bang. So it's a really big deal. Of course, we're going to study in very detail exoplanets, and those are planets we think are habitable in other galaxies, most of nearby galaxies. And we know now there are thousands of them. And we'll also be able to better characterize planets in our own solar system, planetary bodies like Mars. Just a reminder, Webb is a NASA-led mission, but we have two significant international partners, the European Space Agency and the Canadian Space Agency. And Webb was developed across 29 states in the US and 14 countries, primarily in Europe and of course in Canada. After we completed all of the telescope and instrument development at the Goddard Space Flight Center, we shipped it off to Johnson, did all of the environmental testing down there, we did the mechanical testing back at Goddard, and then we shipped out to Northrop Grumman that you see here. On the left is the Sunshield and the spacecraft bus, so we had to integrate the two out there. Can you hear the sound?
Yep.
Oh, great. They didn't work quite this fast. I wish they had. You can see the size of the telescope versus the size of the people, and the different ways they have to work with chair pickers, diving boards, in a clean room, in the bunny suits. So that was a very quick video. That integration took several months. The deployment and testing took even longer than that, much longer. So this was after we had gotten everything integrated. We actually deployed the primary mirror. You can see the primary mirror here is 18 different segments that make up one big mirror. And during launch, you'll see it in the stowed position. The three mirrors on each side are actually folded back in the stowed position. You can see the truss going up from the bottom to the top in a reverse V, and that's the primary mirror. It actually deploys out towards you on orbit. And this is fully deployed Sunshield, as you saw in the video. You can see the primary mirror at the top right there, and you can see the wings folded back. The secondary mirror up top, and the primary mirror, you can see the wings folded back. Same thing, folded stowed telescope. You see the Sunshield actually folded up on each side of the telescope, and it's getting ready for the covers so it can go into the final observatory stow position. You can see it fully stowed here, and that's the configuration that actually is launched in on top of the rocket. So last, I'm losing track of time, September, we shipped off to from LA, Redondo Beach in Southern California, from Northrop Grumman. You can see on the top left, that's the big shipping container connected to the truck. and that truck drove us down to Seal Beach, just south of LA. And in the top middle, that's the ship that drove us, that shipped us down along the Pacific coast through the Panama Canal into French Guiana, Peru, French Guiana. And it's coming out of the boat on the top right. Everything, the truck and all, were in the bottom of the boat. It's a pretty big boat. And that ship is actually used to ship European hardware, excuse me, from Europe to French Guiana for launch. On the bottom left is the launch facility in French Guiana. If you look real close on the bottom right, you can see the truck with the shipping container heading towards the base. In the bottom middle, we're going into the processing facility. We ship in the horizontal position. You can see on the bottom right, we've actually taken it out of the container. Now it's in the stowed position, and that's when we start all the processing to get it ready to make it to the rocket. On the left, it's made it to the rocket, to the top of the rocket. You can see the people at the base. You can see the shower curtains around the thing to keep everything nice and clean. You don't want particulate to get on the mirrors. On the top right, that's the spacecraft fairing, or the rocket fairing, that goes over top of the spacecraft, and that's how it's launched. You can see on the bottom right, you can see the spacecraft just under that, and the fairing actually comes over the top, it comes down, and it's made it to the top of the rocket to encapsulate the spacecraft. You'll see that again in just a minute in the video. So this was launch day, Christmas morning. I think there were more TV sets on Christmas morning in the history of mankind. I haven't done a survey, but I think that's the case. Can't tell you how many people I've talked to that said, hey, got grandma up on Christmas morning, got the kids up, and we watched the launch. And these are people I've talked to from around the world. So this is the launch complex in French Guiana. And this was Christmas morning. And this, when I did this pre-launch interview, it was about 30 minutes before launch, and then I had to go back and get on console. So a really good morning. You can see the size of the rocket here. Just looking from the bottom going up to the top of the rocket, where you will see the spacecraft or satellite connected to the top of the rocket. Want to look out there? And that's about 15 stories up. See the fairing coming over to encapsulate. This was December 23rd. We rolled out to the pad. It was very rainy and windy, about 3 days in a row there.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
This was after separation from the rocket. You can see the bottom of the spacecraft still moving away. That's the solar ray deploying, which we did not expect to see in the separation video.
The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
So a couple of things of note. You heard during the count, it was in French. So the ESA supplied the rocket. That was an Ariane 5 from Arianespace. and everything they do there is in French. Of course, all of our communication is in English, so mostly very good English speakers. But the country is French, and most of the processes and procedures are in French. So after launch, this is the Space Telescope Science Institute in Baltimore, Maryland, by Johns Hopkins. That's where we have the ground segment and mission operations center. So after launch, they take control of the spacecraft, and that's where we're doing the commissioning from. And for the life of the mission operations will be done from here. You can see some of the folks on console, and this is a 24/7 operation. So after launch, this is a simulated deployment. We had what we call the 29 days on the edge, where all the deployments had to work based on a certain timeline, as you can see there. We had some flexibility. On the bottom, you can see the spacecraft heading out past the moon on its way to Lagrange point 2, and while all of these deployments are taking place. So we had to build this so we could fold it up so it could fit inside the rocket fairing, and everything had to deploy on orbit for the most part flawlessly, and it did. So we completed that in the first 29 days, and that also got us out to our destination orbit, Lagrange point 2, L2, we call it, 1,000,000 miles from Earth. You can see it here. It's 1,000,000 miles out. This is in kilometers out to L2, and we want to make sure that the warm side of the spacecraft always faces the Earth, Sun, and the Moon, because we want to keep it nice and warm, and the telescope side is always facing away into dark, cold space. And we have that big tennis court size Sunshield that you saw deploying, unfolding. That's to protect one side to stay very hot and the other side to stay extremely cold. And right now we're about 400 degrees below zero cold on the telescope side. Pretty amazing. And the orientation never changes. The telescope itself will never face the sun and the Earth, because you want to look off into cold, very dark space so you can find extremely faint light and pick up heat signatures as well. And this is that L2 orbit. You can see the orientation stays the same as it orbits. That orbit is stable, so we don't have to use fuel to keep it in its orbit. Or at least very minimal fuel, and it also is away from the heat and light of Earth and the sun. So after we got all the deployments done, the first thing was to align and focus the telescope. We used primarily one of the science instruments to do that, called Nearcam, near infrared camera, and this was one of the first what we call engineering images, non-science related, so we can do all the alignment and focusing. So this is one of the first stars that images that we took. It's extremely bright. This took less than a minute and about 70 times faster than what Hubble can do, which still blows my mind with that kind of capability. This same thing that's zoomed in very close, and you can see galaxies in the background there. And Nearcam also took a selfie. There's a mode where we can do that from the secondary mirror. And of course, once we go into science mode, then this capability is not available to us. So it's a very neat thing to have as we do the focusing. And so we have we've completed all the focusing of the mirror, and The mirrors align with all of the instruments. So we've completed another big phase, deployments and the mirror alignment and focusing. And you'll see a little bit of this here. These are some of the images. This was last Friday at the Institute. This was a meeting to confirm that we completed all the alignments.
Give everybody an opportunity to concur, but.
Yep, I concur.
Okay.
More than one person was polled, but just a little snippet. I was sitting in the back left there. And this is the spacecraft, and all the instruments get down to their cold temperatures. So our total commissioning time is 6 months, and we're about 4 months into that. So again, we've completed deployment, we've completed mirror alignment and focusing, and you can see what the areas we're here. So we're about 125 days or so through commissioning, and the total commissioning time is about 180 days. So we have about 2 months to go. And now we're in the phase called instrument commissioning. These are the science instruments that will take the images from the mirror and process it into what we will actually see here on the ground. And that's so another 60 days or so. One more quick video. This one is a little bit longer. So this, we haven't talked a lot about the instruments, what they actually do. We've talked a lot about the big observatory, the mirror. We've talked about the Sunshield, the orientation, the orbits, how we put it all together. And we haven't talked a lot about the instruments. So this will give you some really good insight into the instruments. For the ones who may have seen this before, this is at least this building, building 28. That's the high bay where the instrument package and telescope were built and integrated. And that's building 28. That's also that same high bay that Hubble was developed in.
In a specialized building like this, NASA built a new machine for science. The James Webb Space Telescope is a complex collection of scientific instruments designed to tackle some of the biggest questions in astrophysics. Webb has 4 instruments contained within the Integrated Science Instrument Module, or ISIM, located directly behind the primary mirror. They're all designed to observe an infrared light, which is invisible to human eyes. Infrared is a longer wavelength of light located on the electromagnetic spectrum, just beyond light human eyes can see. We feel infrared light as heat. Each of the instruments play a different scientific role. The near-infrared camera, or Nearcam, is the main imaging system. Nearcam will look back in time to study the formation of the earliest stars and galaxies. One aspect of its design includes the ability to block light from a bright object, so much that a much dimmer object nearby might be observed. This means that in addition to looking at distant objects from the earliest days of the universe, scientists hope to study aspects of planets orbiting nearby stars. The Nearcam instrument also plays a key role in the process of aligning Webb's 18 primary mirrors, its secondary mirror, and its fine steering mirror using a clever technique called wavefront sensing and control. One of the best ways to find out new information about distant objects is through analysis of the light those objects emit. The Near-Infrared Spectrograph, or NIRSPEC, will collect spectral information about distant objects in order to determine their composition, temperature, velocities, and mass. To do this, NIRSPEC will employ a unique technology called a micro-shutter array. It's an extraordinary collection of mechanical shutters, each barely wider than the thickness of a human hair, that can simultaneously collect high-resolution data from up to 100 distant objects. Different wavelengths of light present different information, and each of Webb's scientific instruments pursues different slices within the infrared spectrum. The mid-infrared instrument, or MIRI, will look at wavelengths of light that are a little longer than the other instruments will observe. Not only will this enable extraordinary images, but it will also allow scientists to search for planets around distant stars, dust warmed by starlight in protoplanetary disks, and comets and asteroids in our own solar neighborhood. MIRI is the coldest instrument on Webb, operating at just 6 degrees Celsius or 11 degrees Fahrenheit above absolute zero. The fourth part of Webb's instrument suite is 2 instruments. The near-infrared imager and slitless spectrograph, working in concert with the fine guidance sensor, will look for ancient light in the universe and information about planets around distant stars. The fine guidance sensor helps keep Webb pointed and perfectly steady during all observations. Together, these instruments and the technologies that will enable them will make up one of the most complex and ambitious undertakings in the history of humanity. This is NASA's James Webb Space Telescope.
So that brings us to the end. So in a couple of months, we will put out what we call first light or first images, and those will be the first scientific images from James Webb. And that's the beginning of many, many years of magnificent science that